In this video, we are going to continue with November 2011 Part B essay, precisely the West African Senior School Certificate Examination Chemistry Paper 2, question 5 and 6. In this section, section 2, for candidates in Ghana only, answer one question from this section. No mark will be awarded for answering questions not peculiar to your own country. 5A, what is fermentation? Before we continue with our topic, I want to appreciate those of you who have taken your time to subscribe to this channel. But for those of you who haven't subscribed to my channel, please like this video, share to other learners, and take some time to subscribe to this channel so that other subsequent papers that we are going to be solving will come directly to you. My special gratitude to myschoolgist.com for making available the papers to us. Thank you very much for taking your time to subscribe to my channel. Let's get started. We're starting with question number 1, number 5A. 5A1. What is fermentation? Fermentation. A total of it, all these from A1, A2, A3, A4, then 1 and 2 make a total of 9 marks. You don't have to write much, just go straight to the point, because we have just 9 marks for all this. But if you have space and time, it's good, you write. So fermentation is a process by which carbohydrates are broken down by enzymes in yeast to produce glucose. The enzymes in the yeast will further catalyze the breakdown of the glucose to form ethanol and carbon dioxide. This is carried out at a temperature of 37 degrees Celsius and under anaerobic conditions. So you need to give the brief definition and the condition under which this reaction takes place, fermentation takes place. If you have time, you can include the equation. So just see what I've written here. Just see what has been presented here. I said fermentation. This is a process by which carbohydrates are broken down by enzymes in yeast to produce a glucose. The enzymes in yeast further catalyze the breakdown of glucose to form ethanol and carbon dioxide. This is carried out at a temperature of 37 degrees Celsius and under anaerobic conditions. Okay. Question number, the second part of it. Write an equation for the fermentation of glucose. Good. You just have to write the equation. You are given the definition. The equation is there, it's just there. The equation here is C6, that is 5A2, C6H12O6. The yeast is there as a catalyst at 37 degrees Celsius. We will have ethanol 2 moles of ethanol and 2 moles of carbon dioxide. Make sure your equation is balanced, please. Now, the third question is, what substance must be added to glucose solution to make it ferment? The substance that will catalyze, or the substance that will enhance the fermentation of glucose, is yeast. Remember, I said the enzyme in yeast will catalyze the breakdown of glucose to form ethanol and carbon dioxide. Ethanol and carbon dioxide are the product of fermentation. So 5A3 is yeast. Yeast is the substance that must be added to glucose to enable it to ferment. 5A4 complete and balance the following chemical equations. Complete and balance the following chemical equations. You have propan-1-ol. You can say propanol, that's propan-1-ol. Propan-1-ol with sulfuric acid undergoing heating. What will be that is concentrated sulfuric acid. What will be the product? Remember that concentrated sulfuric acid is used as a dehydrating agent. It's a dehydrating agent. It dehydrates alcohol to produce alkenes. So the outcome of this will be an alkene and a molecule of water. So the alkene that can be produced here is propene. Is propene. So now this is the equation. So that is the equation. There we will have a propene and a molecule of water that is being produced. Then the other reaction was ethanoic acid plus methanol. Ethanoic acid and methanol. The methanol, when a carboxylic acid reacts with an alcohol, the resultant is an ester that is being formed. It's a condensation reaction resulting in the formation of an ester with a molecule of water being released. That's condensation. Obviously, the catalyst in this reaction here is concentrated sulfuric acid. So this is how it is. When carboxylic acid reacts with, that is 5,2, when it reacts with ethanoic acid, carboxylic acid reacts with ethanol, concentrated sulfuric acid, and under heating, and the name of the product will be, it is methyl ethanoate. Methyl ethanoate and water that is being formed. So now let's go to 5B. 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 Explain why ethanol is completely miscible with water. That is, it can mix without you identifying that this is ethanol or this is water. It can mix very well. Explain why ethanol is completely miscible with water. Yes, the answer is simple. It has to do with intermolecular hydrogen bonds, intermolecular hydrogen bonds, formation of intermolecular hydrogen bonds. That is what will make them to mix properly or to dissolve properly. So we can now say ethanol is completely miscible with water because it forms intermolecular hydrogen bonds bonds with water molecule. This is how it is. Finish. When you write like that and you have space and time, this is a molecule of ethanol, and with water molecule, what happens? There is what we call hydrogen bonds. A bond formed when hydrogen attached to a highly electronegative element, then attaching itself to a second electronegative element, to a second hydrogen which is attached to a highly electronegative element. These are hydrogen bonds, and you see how they are being indicated. This is water, and water is attaching itself to this one. There are two lone pairs of electrons here. That is why it is attaching itself here. So that is why you see them like that. Hydrogen and oxygen attaching itself here, and this one. That is why we say they are hydrogen bonds that are formed. Hydrogen bonds are formed when, because of the presence of intermolecular hydrogen bond. That is what makes it to be miscible with water. Question number 5. After 5b, we will go to 5c. 5c is on biotechnology. Biotechnology. What is biotechnology? What is biotechnology? That is C1. What is biotechnology? That is C1. Biotechnology, for the purpose of revision, you see with the increasing knowledge of technology, you see what has been going on nowadays. We increase agricultural yield, or our agricultural yield or produce are higher nowadays than before, both in with crops, with animals, and even human beings, because of biotechnology. So, biotechnology, what is biotechnology? We can say that is 5C1. Biotechnology is the application of biological organisms. Application of biological organisms, system, or process to manufacturing and the service industry. The application of biological organisms, systems, or process to manufacturing and the service industry. For instance, I am saying the use of genetics in agriculture. With this one, there's greater yield or greater agricultural produce. The use of genetics in in vitro culture in animals, giving us different breeds. So that is just a brief definition of biotechnology. Then C2. C2 is 5C2. Distinguish between fine chemicals and heavy chemicals. What are fine chemicals? Fine chemicals, just from the word fine and heavy, you will notice that fine chemicals distinguish between fine chemicals and heavy chemicals. The first one has to do with the quantity, the quantity and the quality. For fine chemicals, these are chemicals produced in small quantities for specific purposes. Chemicals produced in small quantities for specific purposes. Then for heavy chemicals, chemicals used extensively in industries. They are used extensively in industries. The second one, they are of high degree of purity. Fine chemicals are of high degree of purity. For example, we are talking of biocides, active ingredients in medicine, all the active ingredients in medications. These are what we call fine chemicals. And special chemicals. So we say they are of high degree of purity. Biocides, active ingredients in medications, and specialty chemicals. Again, for heavy chemicals, they are produced in large quantities. For instance, sulfuric acid. that is used in industries and in laboratories, science laboratories. Nitrogen, oxygen, ethylene, propylene. These are heavy chemicals that are produced in large quantities. Okay, let's go to C3. C3, C3, mention the major raw materials used. Mention the major raw material used in the large-scale production of each of the following. Mention the major raw material used in the large-scale production of each of the following. So the raw material used in large-scale production for cement and for tires. What are the raw materials for cement? What are the raw materials for tires? Let's have it here. The raw materials that are required for large-scale production of cement, these are the major ones. We have the limestone, that is a calcium carbonate. We have clay. We have marl. We have silicate. We have iron ore, that is iron 3 oxide. We have aluminum. These are the major raw materials that are required for the large-scale production of cement. Secondly, the other raw materials that are needed for large-scale production of tires include, we have rubber. The rubber could be natural or it could be synthetic. We have carbon black. We have sulfur. We have steel. We have nylon, petroleum, and silica. These are the raw materials that are needed for the production of tire. Let's go to 5D. Question 5D1. 5D1 lists 3 chemical properties of acids. What are the 3 chemical properties of acids? 3 chemical properties of acids and the uses of sulfuric acid. The 3 chemical properties of acids. There are 3 major chemical properties of acids. The first chemical property of acid is acid react with metal. Acid will react with metal. They react with metal that are above hydrogen in the reactivity series to form salt solution and the hydrogen gas being released. So the acid react with metal above hydrogen, metals that are higher up in the reactivity series than hydrogen. They will react with them to produce salt and hydrogen gas. 2, acid react with carbonates. Acid react with carbonates to form salt, water, and carbon dioxide. 3, acid react with bases to form salt and water. Acid will react with bases to form salt and water, except ammonia. Except ammonia, because ammonia will only react with acid to produce ammonium salts. So their reactivity with metal, their reactivity with carbonates, and their reactivity with bases. That's just all. Okay. Uses of sulfuric acid. That was 5D2. Large-scale uses of sulfuric acid. What are the large-scale uses of sulfuric acid? Sulfuric acid is used for making fertilizers. Sulfuric acid is also used for making detergents. Sulfuric acid is also used for making paint, dyes, and synthetic fibers. It is also used as acid in car batteries. Okay, we go to 5D3. 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 Write a chemical equation for the action of heat on each of the following. Action of heat on silver nitrate, salt. Action of heat on lead nitrate, salt. What are the action? Okay, chemical equation to show the reaction. Okay, They are all decomposition reactions. They are all decomposition reactions. So when silver nitrate is heated at the temperature of 250 degrees Celsius to 440, silver solid is formed, oxygen is released, and nitrogen dioxide is also gas is also formed. Lead nitrate, when it is heated, lead oxide is being formed, oxygen is also being formed, oxygen is being released, and the nitrogen dioxide is also being released. These are the action of heat on these two substances. They undergo decomposition under heat. So we will be going to question number 6. And we will be going to question number 6. We are starting with question number 6. Before we continue, if you haven't subscribed to our channel, please like the video, share to other learners, and most importantly, take some time and subscribe to my channel. Thank you. Question number 6A. 1. Define hybridization. 2. Explain briefly how sp3 hybrid orbitals are formed. Define hybridization. And 2. Explain briefly how sp3 hybrid orbitals are formed. Okay, what is hybridization? Hybridization is the mixing of atomic orbitals to produce new set of hybrid orbitals of equivalent energies. Once more, I'm saying that hybridization is the mixing of atomic orbitals to produce a new set of hybrid orbitals of equivalent energies. Simple. 2. Explain briefly how sp3 hybrid orbitals are formed. Here, in this type of reaction here, you need to write a step by step, just as I'm going to explain to you how an sp3 hybrid orbitals are formed. Let me show you how you can do it. Okay. Question number 6. I talk about them is the mixing of atomic orbitals to produce a new set of hybrid orbitals of equivalent energies. Okay, formation of sp3 hybrid orbital using methane. Methane is an example of an sp3 hybrid orbital. So, formation of an sp3 hybrid orbital. The formation of an sp3 hybrid orbital using methane as an example. The first thing is step number 1. In step number 1 for this formation, see how it works. In step number 1 for this formation, when you write the electronic configuration of carbon, I am using carbon as an example. I'm using methane as an example. How an sp3 hybrid orbital is formed. I'm using carbon as an example. So the first step is write the electronic configuration of carbon. It is 1s2, 2s2, 2p2. Now the second step is step 2, electrons in boxes. So you need to write electrons in boxes. Now the 2s orbital and the 2p orbital. Remember the 2p orbital has other suborbitals. We have 2px, 2p x, y, and z. So each of the orbital need to have a maximum of 2 electrons. And we have to use the Hund principle in filling it. So now, we have written electron in boxes. We have 2s orbital. The 2p is a bit higher up than, and has a higher energy level than this one, even though they are of the same energy level, but the 2p is a bit up. So 2s has the first 2 electrons are filled. Where we are, the first 2 electrons are filled. So we are dealing with only the 2s and this one. We are dealing only with the 2s and the 2p. We are dealing only with the 2s and the 2p. So 2s is 2s2 and the 2p2. So the 2s has 2 electrons. It is filled. We go to the 2p. There are only 2 electrons there because carbon has atomic number of 6. So the first 1s2, 2s2, 2p2. So filling it, we are concentrating only on the 2s and the 2p. Now the 2s is filled. Let's go to the 2p orbital. The first 2 orbitals are filled. We have an empty orbital. So because of this empty orbital, we go to step 3, promotion of electron to higher orbitals. We need to promote an electron. So now this electron, one of the electrons here, will need to come here to make this half filled. That what we call promotion of electrons to higher orbitals. This is what is happening here. Now we have promoted 1 electron from the 2s to the 2p. We are now coming to what we call mixing of, I said, because we are dealing with the 2s and the 2p. As I told you that hybridization is the mixing of atomic orbital. We are now mixing the s orbital and the p orbital. Mixing of atomic orbitals to produce a new set of hybrid orbitals of equivalent energies. Okay, we are now taking 1 electron from here to this one. We are now mixing orbitals now. Now, when we promote 1 electron from here to this one, the 2p orbital become half filled and the 2s is half filled. This is how it works. Now, these 2 s orbitals, we can now say here that mixing of, that is step number 4. Step number 4 now is, step number 4, mixing of s and p orbital to form a new set of hybrid orbitals of equivalent energy. Okay, it is the s and the p3 orbital that are mixed now. So now we have, this is the s orbital, we have 1 electron, and this is the p orbital that has 3 electrons. So that is the s that has 1 electron and the p that has 3 electrons, all together giving us an sp3 orbital. Or you can put it like this: in electron in orbitals, this is the s and the px, y, and the z. With this one here, it tells us that carbon has 4 electrons in its outermost shell. And these 4 electrons, it can now bond it with any other atom that has 1 electron. And that is why hydrogen is the only one that can now donate one electron to fill the orbital. Hydrogen can donate 1 electron here, another hydrogen here, another hydrogen here, another hydrogen here, giving us CH4, which is methane, undergoing an sp3 hybridization. So we now say this can then form covalent bonds with hydrogen atoms to complete their electrons in orbitals. And that's just all. Follow the first steps. Use methane as an example for the formation of sp3 hybrid orbital. Write electronic configuration of carbon. Write electron in boxes. But please, we are with 2s and the 2p orbital. We don't go to 1s2. Okay, promotion of electron to fill the last orbital of the 2p. Now, we now have half-filled s and half-filled p orbital. Mixing of orbitals to form the sp3. Then, this is now available for covalent bonding with hydrogen atom. That is just what you are supposed to do. That is just what you are supposed to do. If you do like that, the examiner gives you all the marks. Now, let's go to the next question, which is, after that, we now go to question number, we go to 6b. Consider the equilibrium reaction represented by the following equation. So, sulfur dioxide plus oxygen to give you sulfur trioxide. This reaction is exothermic. It is exothermic. X minus X kilojoule per mole. Write an expression for the equilibrium constant Kp. That's for the partial pressure Kp, because all these are gaseous reactions. So Kp equilibrium constant Kp, this is how equilibrium constant Kp for that reaction is written. This is how Kp is equals to P square, because there are two modes of this one, P square, divided, that is for the product all over reactant, but it is P square divided by P square divided by P square, that is, there are two modes of sulfur dioxide and then P oxygen. That is how you can write it. Pressure, because they are all gases. That is the expression. Now let's go to the other part of it. The other part of it is sketch the energy profile diagram. Sketch the energy profile diagram for the forward reaction. Indicating the position of reactants and products, activated complex, enthalpy change, activation energy. Sketch the energy profile diagram. Sketch the energy profile diagram for the forward reaction, indicating the position of reactants and products, activated complex, enthalpy change, activation energy. So this reaction is an exothermic reaction. We need to sketch a profile diagram, an energy profile diagram for sulfur dioxide, 2 moles of sulfur dioxide plus oxygen, to give the product 2 moles of sulfur trioxide. And it must be an exothermic reaction. This is how an energy profile diagram for this can look like. Okay, that is a 6B2. This is an energy profile diagram. This is an energy profile diagram for the reaction. We have sulfur dioxide plus oxygen to give us sulfur trioxide. And we said it was an exothermic reaction. Being an exothermic reaction, remember that the energy of the product is lower than the energy of the reactants. So we have been told to indicate the activated complex. This is the activated complex where there is bond. This is the activated complex where there's rearrangement of bonds. At this level, activated complex, there's rearrangement of bonds. This is the activation energy. This is the activation energy. This is the activation energy EA. From here to right to this level, this is activation energy. Then reactants, these are the reactants here, sulfur dioxide plus oxygen, all gases. Product, this is sulfur trioxide. Okay, the enthalpy change. The enthalpy change from the product to the reactant, it is negative, minus X kilojoule per mole. And this is an exothermic reaction. This is this here. From this level to this level, that's why the difference, this difference here is what we call the enthalpy change, energy change. I don't say enthalpy change or energy change, which is exothermic. And you see, this is the reaction pathway. This is the reaction pathway. And this, if you can draw this, label it, energy of reactant, energy of product, everything, activated complex, the examiner, and give the enthalpy change for in kilojoule per mole, the examiner will give you all your marks. Okay, let's go to the next question. The next question is C. Calculate the pH of a solution containing 4.0 times 10 to the minus 5 mole per dm cube hydrogen ion. We need to calculate this pH. 2. Indicate whether the solution is acidic or basic. Give a reason for your answer. The calculation and the reason altogether 5 marks. K, C1 and 2. This is how you can solve it. How you can calculate your pH. The pH is a negative log of hydrogen ion concentration. We have been given the concentration. So the pH here is what? The pH of 4.0 times 10 to the minus 5 mole per dm cube. Okay, the pH of the hydrogen ion concentration, this is the hydrogen ion concentration. pH is negative log of hydrogen ion concentration. Okay, negative log of the hydrogen ion concentration has been given as this mole per dm cube, which is this one. So we now find the negative log to base 10 of this concentration. And if we do that, the pH of the solution is 4.40. Now, they ask or indicate whether it is acidic or basic. This solution is acidic. It is acidic because the concentration of hydrogen ion in solution is small. The concentration, because the smaller this I said the solution is acidic because the concentration of hydrogen ion in solution is small. Or you can say it is acidic because the pH is below 7. The pH below 7. So it is acidic. Okay, let's go to the other section of the question. 6D. The 6D part of the question. 6D part of the question. The 6D part of the question says, 6D part of the question. Give 3 differences between the solubilities. Differences between the solubilities of solids in liquid and the solubility of gases in liquids. Solids and gases. Give the difference between the solubility of solids and the gases. How soluble are these in liquids? Let's have them. Let's have their solubilities for solid and for gases. Okay. Solubility of solids and gases in liquids. Now we are going to compare them in three different forms based on their temperature, using the same temperature, using pressure, and using the surface area. So now, if we use this temperature, solubility of gas in a liquid, what happens? Solubility of gases in liquid, temperature. Solubility decreases with increase in temperature. For gases, their solubility decreases with increase in temperature. But for solids, solubility increases with increase in temperature. 2. Pressure. Solubility of gases increases with increase in pressure. For gases, I said solubility increases with increase in pressure. But for solid, pressure has no effect on solubility of solid in liquids. And the last one is surface area. Surface area. For gases, surface area has no effect. For gases, surface area has no effect on their solubility. Surface area has no effect on the solubility of gases in liquids. But for solids, solubility increases with increase in surface area. Solubility of solid increases with increase in surface area. So that is what I have for you for this paper. Thank you for listening. It's been a pleasure to have you today. Thank you very much. Thank you, thank you, thank you. Thank you. Once more, our priority is to see you succeed in your exams. So, for those of you who haven't subscribed to our channel, please like the video, share to other learners, and most importantly, take some time and subscribe to the channel. Thank you. Have a nice day.